So today we're going to look at buffer solutions. Okay. Now what exactly is a buffer solution? Okay. A buffer solution is a solution. Okay, it is a solution that resists changes in pH when small amounts of acid or alkali are added to it. And small amounts of acids or alkali are added to it. When we talk about buffers, we have two types. Okay, we have acidic buffers and alkaline or basic buffers. We're going to start with acidic buffers. Now, what exactly is an acidic buffer? Okay, an acidic buffer, okay, is a solution of a weak acid and its conjugate base. Right? And normally what we do is we use a salt of the conjugate base. Okay, the conjugate base, obviously if it's a weak acid, right, it very partially ionizes to form conjugate base. So what we use is we use a salt of the conjugate base, okay, to make a buffer solution. So we can make a buffer solution by using a weak acid and a salt of its conjugate base Both the weak acid and its conjugate base will be found in relatively large quantities. If you just use a weak acid, obviously it's not a buffer solution because the weak acid only partially ionizes, so you actually have a very small amount of conjugate base. So you're going to use a salt of the conjugate base, okay, and that way you have large amounts of both. 20 centimeter cube of 0.1 mole per dm cube, 20 cm cube of 0.1 mole per dm cube sodium hydroxide is mixed with 40 cm cube of 0.15 mole per dm cube ethanoic acid. Okay, ethanoic acid, that is CH3CO2H. Okay. And the question is, we want to find the pH of the solution obtained. Okay. We want to find the pH of the solution obtained, and the Ka for ethanoic acid, okay, is 1.74 into 10 to the power of -5 moles per decimeter cube. Okay. This is the Ka for ethanoic acid. So over here we have sodium hydroxide reacting with ethanoic acid to form what? A salt, right, and water, right? This is a neutralization reaction. Right? We have sodium ethanoate and H2O as the products, right? So these are our products here, right? We have CH3CO2 minus Na plus, that's CH3CO2 Na, right? That's sodium ethanoate and water, which is H2O. Now over here, right, we want to find the pH of the solution, right? And they've given us the Ka, the acid dissociation constant. So we know that the Ka for ethanoic acid is the concentration of H plus times the concentration of CH3CO2 minus divided by the concentration of CH3CO2H, right? This is, we can find the concentration of H plus if we know these two, and we also know the Ka here, right? So we want to find the pH, we want to find the concentration of H plus ions. So this is our goal. But we don't know the final concentration of ethanoate ions, we don't know the final concentration of ethanoic acid. So what we're going to do first is we're going to figure out how much ethanoic acid is left over and how many moles of ethanoate ions we have, right? So for that, we're going to do a molar calculation. So over here, we know that the number of moles of NaOH is just the concentration times the volume, right? The number of moles of NaOH is, concentration is 0.1 and the volume is 20 cm cube, so that's 0.02 decimeter cube. So we have 0.002 moles of NaOH. We have 0.002 moles of NaOH. Similarly, we can find the number of moles of ethanoic acid, right? We know that the number of moles of ethanoic acid is concentration times volume, so that will be 0.15, that's the concentration, times the volume is 0.04 decimeter cube, right? That's 40 cm cube. So that is 0.006 moles. So now these two react in a 1:1 ratio. So we know that ethanoic acid is in excess because all the NaOH will react, right? 0.002 moles will react, whereas ethanoic acid only 0.002 moles will react, right? Because once the NaOH reacts, we'll have ethanoic acid left over, right? The reaction will stop. So we know that after the reaction takes place, we have 0 moles of NaOH left over, but we have 0.004 moles of ethanoic acid left over. Again, our goal is to figure out the concentration of ethanoic acid and the concentration of ethanoate ion. Now we know the number of moles of ethanoic acid. We also know that here we're making ethanoate ions, right? We're making a salt of the conjugate base. And how many moles are we producing of this? 0.002 moles, right? For every mole of this that reacts, right? 1:1 ratio. For every mole of these two that react, you have 1 mole of this being produced. So we know that we're producing, or we have after the reaction 0.002 moles of ethanoate ions have been produced, right? Or sodium ethanoate has been produced. Now what we see here is that we have a weak acid, and we have a salt of its conjugate base. We have a weak acid and salt of its conjugate base. That means that this type of a solution is an acidic buffer solution. Okay, this is an acidic. Now we have an acidic buffer. So what we have here is a weak acid, right? After this reaction has taken place, we have a weak acid, that's ethanoic acid, right? That partially ionizes to form CH3CO2 minus and H plus ions, right? And we have a salt of its conjugate base, right? Which ionizes completely. It's a salt. It ionizes completely in solution to form CH3CO2 minus and Na plus. So then what we can say here is that we know that we have how many moles of ethanoic acid present? 0.004 moles. We have 0.004 moles of ethanoic acid present. And how many moles do we have of the salt of the conjugate base? 0.002 moles, right? 0.002 moles. And therefore, obviously, we have 0.002 moles of this ethanoate ion, right? Because this ionizes completely. A salt completely dissolves in water and it completely ionizes. So what we want to do now is we want to calculate the pH of this buffer solution, right? We have an acidic buffer and we want to calculate the pH of this buffer solution. We have the expression for Ka, right? But here, because we have a weak acid and a salt of its conjugate base, we know that the weak acid ionizes partially, whereas the salt ionizes completely. So we can assume that all the conjugate base comes from the salt. Okay, so we can assume that we have a negligible amount or pretty much zero amount of conjugate base coming from the weak acid. We also know over here the number of moles of acid, right? We can find the concentration, and we can, again, similar to what we did for weak acids previously, we can say that this ionizes so partially that we can assume that the equilibrium amount of acid is the same as the initial amount. So once we made this buffer solution, we had 0.004 moles of acid, and we can assume that even after it ionizes, we're pretty much left with as much as we started with. Okay, so we can take this as the initial concentration of acid. So over here we know that Ka is equal to 1.74 into 10 to the power of negative 5, and this is equal to the concentration of H plus times the concentration of this conjugate base from the salt. Okay, this conjugate base from the salt, so that will be the concentration is just number of moles per unit volume, right? The number of moles over here is 0.002, and the volume is 60 centimeter cube, right? The final volume of the solution, because you mixed a 20 cm cube and a 40 cm cube solution together. So 60 cm cube and decimeter cube is 0.060, and the number of moles of acid is 0.004, and again the volume is 60 centimeter cube. So that will be 0.060 decimeter cube, right? And what we notice here is actually because they're in the same solution, the volumes cancel each other out. So the volumes cancel each other out. So what you end up with here is, you can say that the concentration of H plus is equal to, right, 0.004 times 1.74 into 10 to the power of negative 5 divided by 0.002. So that comes out to what? The concentration of H plus comes out to 3.48 into 10 to the power of minus 5 moles per decimeter cube. Okay. So now if you want to find the pH, we can simply say pH is just the minus log of H plus concentration. So the pH comes out to 4.46. So now the question is, how does this buffer solution resist changes in pH? In other words, how does this resist changes in pH when small amounts of acid or alkali are added to it? Why is its pH not affected too much? Why is its pH not affected too much when small amounts of acids or alkali are added to it? So again, this kind of a solution where you have an acid and its conjugate base present in relatively large quantities, right? They don't have to be equal, but they're both present in relatively large quantities, right? We have an acid and its conjugate base. That type of a solution will be a buffer solution. It will be able to resist changes in pH. A weak acid and its conjugate base both present in relatively large quantities. Okay. Normally, if you just have a weak acid, right, the base is present in very small quantities. Here, because you formed a salt of the conjugate base in this reaction, right, what we did was, in this particular reaction, what we did was we took an alkali and we reacted it with a weak acid, right? And we had that weak acid in excess. So when we did that, after the reaction, all the NaOH had reacted, all of it reacted, but we had acid left over, and we had made a salt of the conjugate base, right? Which ionizes completely in water, obviously. So the salt of the conjugate base actually exists as aqueous ions, right? So what that means is that now in this solution we have a decent bit of acid left over, and we have a decent amount of conjugate base. From the acid itself, you have a very small amount being formed, and obviously as the concentration of this increases, this equilibrium shifts even further to the left, which means you have very few ethanoate ions coming from the acid, where so we can assume that all the ethanoate ions are coming from the salt. Okay, so this applies specifically for buffers, right? This applies specifically for buffers where you can take the concentration of the conjugate base from the salt. You can assume that the concentration of the conjugate base from the salt is the entire concentration, right? You can assume all the conjugate base is coming from the salt. And obviously, since such a small fraction of the acid ionizes, since it's a weak acid, we can again assume that the final concentration of acid is just the initial concentration in this solution that we formed. Now we know that a buffer solution is a solution that resists changes in pH when small amounts of acid or alkali are added to it, right? So in this particular example, we just calculated the pH of this buffer. It was 4.46, right? And we want to figure out why or how this buffer is able to resist changes in pH when small amounts of acid or alkali are added to it. Okay, so let's say that I have this buffer solution, okay, in a beaker. So I have this buffer solution, right? And what I'm going to do is I'm going to add a small amount of acid to it. So I'm going to add a small amount of right? And what we're saying is that this buffer will resist changes in pH. The pH will decrease, but very, very slightly. So for example, if I add a few drops of H plus, right, the pH would go down by maybe 0.02 or 0.03, but there would be a very, very small decrease in pH. And the reason why is because what we have here is, in this buffer solution, we have a conjugate base that's present in fairly large quantities, right? If it was just a weak acid, right, we'd have a very small quantity of conjugate base. But since we have a salt of the conjugate base, right, which ionizes completely, we have a fairly large amount of conjugate base, right, when the salt ionizes completely. And what that does is, it also shifts this equilibrium. It also shifts this equilibrium to the left, right? So we have a fairly large amount of unionized acid as well. It's already a weak acid. It barely ionizes. And when we increase the concentration of this, right, this equilibrium shifts to the left. So that means it was already fairly unionized, and now it's even less ionized, right? So what we have over here is, right, we have large quantities, right? We have large quantities, right? Fairly significant quantities of an acid and its conjugate base, okay, of this acid and its conjugate base. Now when I add a small amount of H plus ions, to this buffer solution, right, the conjugate base, right, present in fairly large quantities, right, when I add H plus ions, the conjugate base that's present in fairly large quantities reacts with that excess acid that I've added, okay. The conjugate base present in very large quantities in this buffer solution reacts with the amount with that excess H plus that I added, right, and it ends up making what? Ethanoic acid. Now the idea is this: if I add a small amount of H plus, because I have so much conjugate base present, right, it pretty much reacts with all of that H plus that I added, and the concentration of the conjugate base decreases by a very, very small amount, right? It decreases by a very small amount because there's such a large amount present, right? A small amount of acid being added to it barely affects the amount of conjugate base, which means that this increase in the concentration of ethanoic acid is also very, very small. This is also very, very small, right? So we have a very small decrease. We have a very small decrease in the concentration of the conjugate base, and we have a very small increase in the concentration of the acid. So what this means here is that this equilibrium, right, because there's very, very tiny changes in the concentration of acid, right, very slight increase in the concentration of acid, and a very slight decrease in the concentration of the base, right, when that H plus reacts, this equilibrium shifts to the right very, very slightly, right. So the overall effect is a very small increase in the H plus concentration. The overall effect is a very small increase in the H plus concentration. So what that means is that it's not like the pH won't change, but a buffer solution, the job is to make sure that the pH changes by a very small amount if you add a little bit of acid or alkali to it, okay. If you add pure water, for example, the pH would change by a big amount, but in a buffer solution, right, a pH will only change by very little. So in this particular case, when you add a small amount of acid, right, you have a very small increase in the concentration of H plus, which means that you have a very small decrease in the pH. Now the next question that we have is how would this buffer solution resist changes in pH when a small amount of alkali is added? So let's say I add a small amount of hydroxide ions, right, like a small amount of sodium hydroxide or potassium hydroxide. Now when a small amount of alkali is added, to this buffer solution, right, what will happen is, right, we know that the acid is present in fairly large quantities. Now the alkali will react with both. It will react with the acid and it will react with H plus ion. But what we can say is, because large quantities of acid are present, the unionized acid, we can say that hydroxide ions will largely react with the unionized acid, right? So the unionized acid reacts with the hydroxide ions. It reacts with the hydroxide ions, and we end up forming CH3CO2 minus and H2O, right? So the acid, the unionized acid present in large quantities neutralizes the small amount of hydroxide ions that we've added. Now what happens here is, because we have acid present in fairly large quantities in the solution, because this acid barely ionizes, we can say that the concentration of acid, even after this reaction, barely decreases. There's a very, very small decrease. There's a very, very small decrease in the concentration of acid. There's a very, very small decrease in the concentration of acid when it reacts with those excess hydroxide ions. And therefore, obviously, there's a very, very small increase in the concentration of the conjugate base, because we have a large amount of conjugate base present. Again, these two are part of this equilibrium, right? The conjugate base is just a single conjugate base. We have a large amount of conjugate base present, so there's a very small increase, right? A small amount of this reacts, and a small amount of this is produced, right? And what that ends up meaning is that there's a very slight shift. There's a very slight shift of this equilibrium to the left. There's a very slight shift of this equilibrium to the left, and therefore the concentration of H plus decreases. Concentration of H plus decreases very slightly. So we can say that there's a very small decrease in the concentration of H plus, and therefore obviously a very small increase in pH. Now for the purposes of our course, okay, they don't expect you to understand how these equilibria are affected. Okay, the main idea here is the following. Okay, what they expect you to know is that because we have large quantities of an unionized acid present and we have large quantities of a conjugate base present, when we add small amounts of acid or alkali, they have a very negligible effect. They have a very negligible effect on the pH, a very small effect. Okay, so if you add a small amount of acid, because you have a large amount of the conjugate base, that small amount of acid will result in a decrease in pH, but it will be a very small decrease. It will be a very small increase in H plus concentration. So the idea is, because large quantities of the conjugate base are present, right, it will react with that little bit of acid that you added, and the overall effect in pH will be very small. It will be a very small decrease. Similarly, because you have large quantities of the unionized acid present, if you add a small amount of alkali to it, right, it will react with that unionized acid, right, it will neutralize that excess alkali, right, it will neutralize that excess alkali, and there will be a very, very small increase in pH. So maybe the pH will change by 0.02 or 0.03, right? In the case of when you add an acid, it will decrease very slightly, and if you add an alkali, it will increase very slightly. But this is the explanation that they expect you to give in the exam, is that if I ask you, how does a buffer solution, how does this buffer resist changes in pH when acid is added to it, this is the equation that represents that, right? And if I ask you to write an equation to explain how it resists changes in pH when alkali is added to it, right, it's this equation, because you have large amounts of this and you have large amounts of this. Again, one thing I want to clarify over here is that you still have the same equilibrium. Okay, so here when we produced this salt of the conjugate base, right, that salt obviously ionized in solution to form the conjugate base, we still have the same equilibrium, right? This is still the equilibrium that we have, right? But what we're saying here is that, right, this is actually a buffer solution. Now, instead of just having a weak acid, which will barely ionize to produce the conjugate base, right, because we had a salt of the conjugate base that ionized completely, now we have a solution of an acid in fairly large quantities, right, because it's unionized, largely unionized, and we have a large amount of conjugate base present, right? So now what we have is, we have large quantities of the unionized acid as well as the conjugate base, right? So we have the same equilibrium, right? These two aren't different, right? They're both part of the same equilibrium. So we can assume that for buffer solutions, if we use a salt, we can assume that all the conjugate base comes from the salt, okay? And because you have large quantities of both of these species present, small amounts of acid or alkali will only very slightly affect the pH of the buffer solution. Now to understand what actually happens to the equilibrium here, right? If you add a small amount of acid, here, what you're doing is that you're increasing the concentration of H plus in this equilibrium. When you increase the concentration of H plus very slightly, right, those excess H plus ions react with the conjugate base, and this equilibrium shifts to the left. So we can say that the equilibrium, right, for the acidic buffer, right, shifts to the left. When this equilibrium shifts to the left, that means that the concentration of H plus goes back down. However, the overall effect is that you have a net increase in the concentration of H plus, right? You increase the concentration of H plus when we add a small amount of H plus. This equilibrium shifts to the left. The concentration of H plus decreases again. However, the initial increase outweighs the decrease that you get due to the equilibrium shifting to the left. So the net effect that you have is a very small increase in the concentration of H plus and a very small decrease in the pH. On the other hand, when you add a small amount of alkali, hydroxide ions, okay, they actually react with the ionized H plus. Okay, and that's why we see this following equation as well in the marking scheme as well, right? What's happening here is that the H plus ions react with the hydroxide ions to form water, and that results in a decrease in the concentration of H plus. Now when the concentration of H plus decreases, right, this equilibrium would shift to the right. So we can say here the equilibrium shifts to the right. Equilibrium shifts to the right. And when the equilibrium shifts to the right, the concentration of H plus goes back up. However, the initial decrease outweighs the increase that we get due to the equilibrium shifting to the right. So the overall effect that we have is a very small decrease in the concentration of H plus and therefore a very small increase in the pH. So the previous explanation that I gave you in terms of understanding the equilibria, okay, they were oversimplifications. They were oversimplifications just to understand, okay, why we have a very small increase in H plus concentration or a very small decrease in H plus concentration, okay. We simply assumed that whatever is present was in large quantities would directly react with the H plus and the OH minus. However, okay, when we add a small amount of acid or alkali, they affect the direction of the equilibrium in the following ways. Okay, if you add a small amount of H plus to an acidic buffer, you will shift the equilibrium for that acidic buffer to the left. Okay, and when you add a small amount of hydroxide ions to an acidic buffer, you will shift the equilibrium for that acidic buffer to the